So today we're going to be looking at the reactions of acyl chlorides, okay, and the mechanism for those reactions. So we're going to start with the hydrolysis of acyl chlorides, okay. I'm going to start with the hydrolysis of acyl chlorides. Acyl chlorides are readily hydrolyzed by water at room temperature, okay, so they react readily with water at room temperature. So we have an acyl chloride, okay, RCOCl, okay, reacts with H2O to form the carboxylic acid, so RCOOH, or you can say RCO2H, and HCl. The mechanism for this reaction, okay, is known as addition-elimination, okay, also referred to as nucleophilic addition elimination. Okay. Sometimes you'll just see it referred to as addition elimination. So here you have an acyl chloride to begin with. You have an RCOCl. Here H2O is a nucleophile, so we have H2O. Okay, so HO and then H, right? Over here, this carbon atom is partially positive, right? This oxygen is partially negative, and this oxygen is also partially negative, right? So what happens here is the first step is very similar to what you have with nucleophilic addition, right? This oxygen attacks this delta positive carbon, right? And then this pi bond breaks. So what we get is, we get R, C. This oxygen now has an additional lone pair that we're going to show, so O minus. And then we have this oxygen that's bonded to two hydrogens, right, from the H2O. This oxygen has a positive charge, and we have a Cl. To understand why this oxygen has a positive charge, okay, think of it this way. This oxygen had a lone pair of electrons, and when it formed a bond with this carbon, right, in the bond, that pair of electrons are now being shared. So in essence, one electron belongs to the carbon and one electron belongs to the oxygen, whereas initially the oxygen had both the electrons. So in essence, what we're saying is that this oxygen has essentially donated one of its electrons to carbon in the bond. Of course, the overall charge is still neutral, right, because you have a plus and a minus. So you have two neutral species reacting with each other, so the intermediate is still neutral, right? Then what we have in the next step, okay, what we have in the next step is that this pi bond reforms, okay, this pi bond reforms and this CCl bond breaks. Now the reason this happens is that the carbon doesn't want to remain bonded to three highly electronegative atoms. It's bonded to two oxygens and a chlorine. Okay, this is fairly unstable because you have three highly electronegative atoms bonded to this carbon. One of those guys ends up leaving. Chlorine is considered a good leaving group. So what happens is that this bond breaks and this pi bond reforms. So what you end up with here then is you get R, C double bond O, and then you have this guy. And you also have a Cl minus, right? That just broke off. And then what happens is that the Cl minus takes a hydrogen from this OH2 group, okay? And this OH bond breaks and you end up making RC double bond O, OH plus HCl, okay, plus HCl. So here in the first step you have the addition of this nucleophile, right? Hence the name addition. And then in the second step the chloride ion leaves, so we say we have an elimination of Cl, hence the name addition elimination. In essence, what we have is we have an OH group substituting for a Cl, but in nucleophilic substitution we don't have addition take place first. In this case we have addition take place first and then we have the elimination, hence the name addition elimination. So when we talk about nucleophilic substitution of halogenoalkanes, for example, right, we have a saturated carbon atom where substitution is taking place. In acyl chlorides, we have an unsaturated carbon, an sp2 carbon, an unsaturated carbon atom here. So we first have addition, right, of this nucleophile as I've shown here in the first step, and then we have elimination of the Cl, right? The Cl is removed, okay, it leaves over here. So this part is called elimination. So we have addition, elimination. The next reaction that we have is alkaline hydrolysis. Okay, alkaline hydrolysis of acyl chlorides or acyl chlorides. Now, in alkaline hydrolysis, let's say that we had an acyl chloride, RCOCl, reacting with NaOH aqueous, right? In this case, instead of a carboxylic acid, we'll have a salt of the carboxylic acid, right? Because sodium hydroxide is present. So we'll have RCOO minus Na plus, right? That's the salt of the carboxylic acid. And instead of HCl, we'll have NaCl, right? And we'll also have H2O, right? Because HCl is also going to be neutralized by the NaOH, right? So we have NaCl and H2O. If you had to balance this equation, okay, we're going to have 2 NaOH. The ionic equation for this reaction is the acyl chloride, okay, is reacting with hydroxide ions to form the conjugate base of the acid, chloride ions, and H2O. Okay, and again we have 2OH minus. So this is the ionic equation for this reaction, for the ionic equation. So the next reaction that we have for acyl chlorides or acyl chlorides is the reaction with alcohols. Okay. Reaction with alcohols. So when we talk about the reaction with alcohols, okay, the reaction is very similar to what we have with carboxylic acids. Okay, so let's say I have this alcohol, right, and this acyl chloride. Okay, what we end up getting is an esterification reaction. Okay, this oxygen ends up bonding to this carbon. Okay, and HCl is also released in the. For a carboxylic acid, we had the acid losing an OH group and the alcohol losing an H to give us H2O. In this case, the acyl chloride loses the chlorine and the alcohol again loses the H. Okay, so it's pretty much the same as we had for carboxylic acid, but here instead of an OH, we have a Cl being lost. Okay, so this oxygen is actually what bonds to this carbon. So what we end up getting here is this guy, right? We get RCO, and then this carbon bonds to this oxygen, right? And then we have HCl. Okay, so this reaction is referred to as esterification, but it is also referred to as condensation. Okay, now in biology you may have learned that when we talk about condensation, we're only talking about the loss of H2O, but that's not the case. Okay, this is also a condensation reaction. Condensation essentially refers to reactions where two molecules combine to give you a larger molecule and something small is being lost in the process. Okay, so far we've only seen condensation where H2O is being lost, but you can also have condensation reactions where HCl is being lost, for example. So here this reaction is referred to as esterification. It's referred to as esterification, also referred to as condensation. Okay. Let's look at a specific example, right? So let's say we had something like ethanol, okay, reacting with, let's say, propanoyl chloride. Okay, propanoyl chloride. What would our product be? So what we have here is we have CH3, CH2, C double bond O. This C double bond O is from the acyl chloride, right, which loses the chlorine, and this carbon here bonds to this oxygen, right, to form the ester linkage. So we have this carbon bonding to this oxygen. So we have this carbon bonded to this oxygen, which is bonded to a CH2, CH3. This ester is known as ethyl propanoate. Okay, this is ethyl propanoate, right? Again, we have a 2-carbon alcohol, right? That's ethanol here, so that's ethyl. And then we have a 3-carbon acyl chloride, similar to what we have with a 3-carbon acid, right? We get the same ester. We get ethyl propanoate, and this H and this Cl combine to give us HCl. Another thing to note here is that when we talk about esterification between carboxylic acids and alcohols, okay, we use an acid catalyst, and we usually use heat as well, right? We use an acid catalyst, concentrate sulfuric acid as a catalyst, right? If we had a carboxylic acid instead, and we also use heat mildly around 60 degrees Celsius, okay? And we get a reversible reaction when we have carboxylic acids, okay? Acyl chlorides are much more reactive. They react much more readily with alcohols. So this reaction takes place at room temperature, okay? Because this reaction happens at room temperature, it's not a reversible reaction. Okay, it's not a reversible reaction, and we don't need a catalyst here. Okay, so it's much more favorable, right? Acyl chlorides are much more reactive than acids are, carboxylic acids are. Okay, so this esterification happens in much milder conditions than with carboxylic acids. The mechanism for this reaction, okay, pretty much the same mechanism as we had with hydrolysis of acyl chlorides. Okay, it's addition, elimination. Okay, addition, elimination. Also again referred to as nucleophilic addition elimination. Okay, so again we have the same thing, right? We have an acyl chloride. In this case we have propanoyl chloride. So we have CH3, CH2, C double bond O with a Cl. This carbon is partially positive. The oxygen is partially negative. Then here your alcohol will be the nucleophile. So we have ethanol here. So we have CH3, CH2. We have an oxygen, right? Again, this oxygen has a partial negative charge. So in the first step, right, this nucleophile attacks this partially positive carbon, and at the same time the pi bond breaks. This is the addition stage of the reaction, right? So we have addition. So we have CH3, CH2, C with an oxygen. Right now this oxygen has this additional lone pair with a negative charge. And then here we have an oxygen, right, with an H and a CH2, CH3, okay? And we have a positive charge on the oxygen. This is again very similar to what we have with water, but instead in water we had a hydrogen here. In ethanol we have this R group, right? In alcohols we have this R group. In the case of ethanol it's CH3, CH2. And then we have the chlorine, okay? And then what happens next is the elimination stage of the reaction. This pi bond reforms and the chlorine leaves. Okay, this is elimination. So first step, addition, and then we have elimination of the chlorine, hence the name addition elimination. What we end up with here is a CH3, CH2, then we have a C double bond O, okay, and then we have a O, CH2, CH3, and we have an H here. We also have the Cl minus ion that was formed, right? We have that Cl minus, so what it comes here and takes away this H plus. Okay, so the Cl forms a bond with the H and the OH bond breaks, and then we end up with our product, right? We end up with our product. So here we get CH3, CH2, COO, CH2, CH3. This is the structural formula for ethyl propanoate, right? Now if you see COO, that means on the left hand side we have the acid or the acyl chloride group written, and then on the right hand side we have the alcohol part written, right? If you see COO or CO2. The structural formula for this, if you wrote it from right to left, can also be written as CH3, CH2, OCO, CH2, CH3. So if we see an OCO here, right, it means that the alcohol part is written first and then the acid or the acyl chloride part. Okay, so these two are the same. It's the exact same compound. Okay, but here we're talking about the structural formula with the acyl chloride or the acid part written first, and here the alcohol part is written first. Okay, so these two are the exact same thing. So you can write down the structural formula as this or as this, right? And you also get HCl. So now we're going to look at the reaction of acyl chloride with phenols. Okay, so we have the reaction of acyl chlorides with phenols. Okay, And again, when acyl chlorides react with phenols, okay, we make an ester. Okay, so the reaction is esterification. Okay. Again, esterification is just a type of condensation reaction. Okay. So here, for example, I have benzoyl chloride reacting with phenol. Okay. So we have benzoyl chloride. Okay. Okay, and this guy is reacting with phenols. Okay, so phenols react with acyl chlorides to form esters. Okay, however, phenols are not reactive enough. Okay, they're not reactive enough to react with carboxylic acids. Okay, so alcohols can form esters with carboxylic acids under the right conditions as well as acyl chlorides, whereas phenols only form esters with acyl chlorides, not with carboxylic acids. The reason why phenols aren't as reactive as alcohols has to do with the electron density on the OH, right? If you look at phenol versus ethanol, for example, right? We know that in ethanol we have this ethyl group, right? That has a positive inductive effect. It increases the electron density on the oxygen. Whereas with phenols, right? We've learned that we have delocalization of the lone pair, right? Or resonance. And what happens because of this resonance is that some of the electron density is withdrawn away from the oxygen towards the ring. The delocalization of electron density means that there's lesser electron density concentrated on the oxygen, which means that this oxygen is less nucleophilic than the oxygen that we have in ethanol. Lower electron density is not attracted as strongly to partial positive charges. It's not as reactive when it comes to donating its lone pair. Okay, so phenol doesn't donate its lone pair as readily as ethanol does. Hence, it doesn't react with carboxylic acid, but it does react with acyl chlorides. So what we end up getting here again is, right, the acyl chloride loses its carbon and the phenol loses its hydrogen, right? So this carbon here ends up bonding to this oxygen, right? And we also get HCl, right, as a product here. So the product here is we get here is this guy, right? We have a C double bond O, right? We have a C double bond O, and then this guy is bonded to an oxygen. This is bonded to another benzene ring. Okay. So this compound is called phenyl benzoate. Okay, this compound is called phenyl benzoate. And here we also end up getting HCl, right? We also end up getting HCl. So again, benzoate comes from the fact that it's the conjugate base of benzoic acid, right? So this benzene ring with the COO or CO2 is benzoate, and then this benzene ring that came from the phenol, or in this case, right, is the phenyl group. So just like we named esters with alcohol when they form between alcohols and acids or acyl chlorides, right? We write the alcohol part first and then the acid part, right? Here we write the phenol part first, right? That's phenyl, and then the acid part or the acyl chloride part, which is benzoate. Okay. The mechanism for this is the exact same as we had for the reaction of acyl chlorides with alcohols or with water, right? It's called nucleophilic addition elimination. Okay. Or in simple terms, we can refer to this as addition elimination. Okay, addition elimination. Okay. So it's nucleophilic addition elimination, also just referred to as addition elimination. And let's draw the mechanism. Okay, I'm going to write C6H5 to represent the benzene ring. So our acyl chloride here is C6H5 COCl. The carbon here has a partial positive charge. This oxygen here has a partial negative charge. Then we have the phenol, right? So we have C6H5OH, right? This oxygen here has a partial negative charge. It attacks the partially positive carbon, and this pi bond breaks, and we end up making the intermediate, right? This this first step is addition. This first step is addition, right? So we have C6H5. We have a CO, right? This oxygen now has an extra lone pair, okay, with a negative charge. We have this oxygen that's bonded to a C6H5 and an H, right? This oxygen has a positive charge, and then we have the Cl. So next what we have is the pi bond reforms, right? And the chlorine or chloride over here leaves, okay? So this is known as the elimination stage. So we have addition in the first stage and then elimination, okay? And then we end up with C6H5, C double bond O, bonded to an oxygen, bonded to a C6H5, and this oxygen also has a hydrogen, and then that Cl minus takes away this hydrogen, right? And this bond breaks, right? So we end up getting our product. Okay, we end up getting our product, which is C6H5 COO C6H5, and we also have HCl. So we have C6H5 and then COO C6H5. I've written the acyl chloride part first, right? The benzoate part first. If we wrote the phenol part first, right, or the phenyl part first, then it would have been C6H5OCO, okay, C6H5OCO C6H5, okay, C6H5OCO C6H5, okay, they're both the same thing. Now usually what we do is, usually with phenols, okay, because they're relatively less reactive, right, when compared to alcohols, if we want to make an ester, right, by reacting phenol with acyl chlorides, we usually do it in alkaline conditions, okay, we do it in alkaline conditions. So if, for example, I had C6H5OH, right, phenol, and I wanted to react it with, let's say, ethanol chloride, right, so let's say you have CH3COCl, we can carry out this reaction in alkaline conditions as well, okay. And the reason we do it in alkaline conditions is because the reaction occurs more readily in alkaline conditions, okay, it occurs at a much faster rate. So over here, we were to write down the equation for the reaction in alkaline conditions, okay, we would have NaOH, for example, right, and again what we end up making is the ester, right, so we have CH3CO, right, this carbon bonds to this oxygen from the phenol, so we have CH3COO and then C6H5, and we also get NaCl and H2O. So in alkaline solution what happens is that the phenol, okay, it reacts with the NaOH, okay, to form sodium phenoxide, okay, so that's C6H5O minus Na plus and H2O. Right, it's a neutralization reaction, right? So phenol reacts with alkali to form salt and water, and over here the phenoxide ion, right, the conjugate base of phenol, is a much stronger nucleophile than phenol itself. So because phenol is relatively less nucleophilic than ethanol, it's relatively less reactive. Normally in a lab, instead of reacting it directly with acyl chlorides in neutral conditions, we react it in alkaline conditions, okay, because in alkaline conditions we end up making the conjugate base of phenols. This conjugate base of the phenol, right, which is phenoxide ion, okay, this is much more reactive towards the acyl chloride, okay. So then what happens is that once we have this conjugate base, okay, it reacts with the acyl chloride. So the C6H5O negative, right, Na plus, this conjugate base now reacts with the acyl chloride, CH3COCl, and we end up getting CH3COO C6H5, right, the ester, and NaCl. And if you add up reactions 1 and 2 together, right, you get the overall equation that we've written above, right. If you add reactions 1 and 2 together, okay, you're going to get this overall equation that we've written. So that's how this reaction works. Again, the reason why this reaction is carried out in alkaline conditions usually or preferably is because the phenoxide ion is much more reactive towards the acyl chloride, okay? We have greater charge density or electron density on this oxygen versus phenol, right? So it's a better nucleophile and it attacks this partially positive carbon in the acyl chloride much more effectively.